Hey Chem Kids, Campbell here. In our video today, we're going to talk about gases and amount. So we're going to talk about Avogadro's principle, which we mentioned in our last video. We're going to talk a little bit more about it today. And we're also going to talk about the ultimate of gas laws, the ideal gas law. So what Avogadro's found was that regardless of what type of gas it was, if I have an equal volume of gas at the same temperature and pressure, I'm going to have the same number of molecules or moles. Isn't that crazy? It doesn't matter if it's a diatomic gas like oxygen or a polyatomic gas like carbon dioxide or a monoatomic gas like helium. As long as they're under the same temperature and pressure, they have the same volume. Totally cool. Now, what he found, right, which makes sense, is that volume and amount are directly related. Right? If I add more molecules or moles of gas to this balloon, its volume is going to go up. And because they're directly related, right, if I double the number of molecules, I'm going to double the volume. Or maybe I take molecules out and the volume goes down. So his equation, a direct relationship equation, is one divided by the other. So the amount in moles divided by the volume in liters at one condition is equal to the amount in moles divided by the volume in some other condition. All right, our last gas law that I want to talk about is called the ideal gas law. The ideal gas law combines everybody's laws together. All right, I have pressure and volume, Boyle, pressure and temperature, Gay-Lussac, volume and temperature, Charles, and now I have amount, Avogadro. But what's this R? Well, that's actually a constant. So very important that we work in the correct units because the value of the constant R is 0.0821, and the units are liters, atmospheres, moles, Kelvin. So that means every time you work with the ideal gas law, your pressure has to be in atmospheres. Your temperature, of course, has to be in Kelvin, regardless. Your volume has to be in liters, and N is number of moles, so you have to work in moles. So if you are not in these units, you need to convert to these units before you can plug into the ideal gas law. All right, so let's see what that means. I want to know how many grams of nitrogen is required to fill a small room with a volume of 27,000 liters to 1.09 atmosphere at 25 degrees Celsius. All right, so what do we got? We want to know grams, so that's an amount. We have a volume in liters. Good. We have a pressure in atmosphere. We have a temperature, of course, in Celsius, because who measures in Kelvin? But we need to make it to Kelvin. So we're going to list all the things that we have, our pressure, our volume, our amount is what we don't know, but we're going to solve for moles first, right, because N will be in moles, but then we're going to have to calculate grams. There's our constant, and of course temperature, add to 73, so that's 298 Kelvin. Now it's just a matter of plugging and chugging. Plug in your pressure, volume, constant, and temperature. Right, there's our equation. Our unknown is the little amount there, the N. And then we're going to divide by the constant temperature, right? That'll cancel it out from this side, and we'll solve for amount in moles. So do some math. Let's see if you get the right number of moles. If you did this correctly, you should have 1,203 moles of nitrogen. But we're not done because remember I wanted grams. So how do we go from moles to grams? Periodic table, but what do? Do we multiply or divide? So remember we have moles, we multiply. So we're going to convert moles to grams by multiplying by the molar mass of N2. So find nitrogen on your periodic table. Multiply that number 2. Nitrogen's 14. Multiply it by 2. That's 28. So we're going to take 1,203 and we're going to multiply by 28. So that gives us 33,681 grams. Wow, that's a lot of nitrogen. That's a really big room. See you tomorrow.